look at the exterior gateway protocol called BGP, the Border Gateway Protocol. First, we want to take a look at an overview of how BGP operates, and we also want to focus in on the important BGP peerings that we're going to be responsible for creating. Border Gateway Protocol doesn't neatly fit into any category of routing protocol we've discussed thus far in the course. In fact, most engineers like to give it its own category called a path vector exterior gateway protocol. It's kind of like distance vector in its operation, but it has a lot of different parameters that are designed to allow administrative tuning. As we're going to see, this EGP's job is to exchange prefix information between autonomous systems, and it uses an AS to AS paradigm as opposed to the normal hop-by-hop routing paradigm we're used to with our interior gateway protocols. Now, in this first lesson, we're going to take a close look at how BGP uses the transmission control protocol for its transport. It's going to use port 179 for its transport capabilities. Unlike the other protocols that we've looked at, it does not have its own built-in transport mechanisms and will rely heavily upon the transmission control protocol for this purpose. You would have to have a complete and total full mesh of BGP on every single one of your routers in order for you to turn away from an underlying IGP. So really, in most environments and in the CCIE lab environment, we're going to have a required underlying interior gateway protocol. As you'll see, as we move throughout our BGP studies, the underlying interior gateway protocol is going to allow us to find next hops that are reported by the Border Gateway Protocol. So it's going to be this very interesting interplay between the interior gateway and the Border Gateway Protocol that we run over the top of the IGP. And again, so we really don't think about networks as running BGP alone, unless the rare case where it is BGP absolutely running everywhere on every single device. Now, the initial setup of BGP is going to be quite simple. Notice in global configuration mode, we're going to issue the command router BGP followed by the autonomous system number. Now, what's interesting is the routers that we're going to be dealing with in the CCIE certification environment are only going to accept one process per router. So this is going to keep you from inadvertently making a mistake. What is interesting here, though, what we want to watch out for is we got to make sure we are assigning the correct autonomous system. We will see this can get a little tricky when we get into confederations. We want to make sure we're setting up this global process with the correct AS, otherwise we're going to have to rip and replace our entire BGP configuration if we're inadvertently specifying the wrong autonomous system. Notice that once we have our BGP global process activated, we're going to create our BGP peerings using the neighbor command. Now, what's confusing about this is you probably already remember from your CCNP level training that we have interior or IBGP peerings and exterior or EBGP peerings. The command says neighbor and then an IP address, which we'll elaborate on shortly, and then remote AS and the remote AS number. This command really looks like it would only be for EBGP peerings, doesn't it? But this exact neighbor remote AS command is indeed going to be the command you use to make both interior and exterior BGP peerings. If the remote AS you specify is your own AS, well, by definition, you'll create an IBGP peering. If the remote AS you specify is truly a different AS, well, then that will be an EBGP peering you create. So this one neighbor command is indeed the command we'll use for both interior and exterior BGP peerings. So let's think about this from a transmission control protocol perspective, and that's really what you want to do when you think about the inner workings of the BGP peering session. We're going to issue the command, let's say, neighbor 1234 remote AS100. What this is going to do behind the scenes is it's going to cause our device to start listening for a neighboring device whose address is 1234. That's going to be the source IP address that we're going to be looking for. And we're going to be looking for that device to start a TCP session at port 179. So we're essentially looking for a TCP server. You can think of it as the BGP server in the relationship to initiate or to rather really begin this session using port 179. We also locally initiate the session to 1234 at port 179. So we're kind of prompting the neighbor, hey, become a server and respond to us from the IP address 1234 and from the source port 179 so we can agree upon this BGP peering that we are going to create. As you know, there must be let's call them symmetric neighbor statements on each device, right? And these neighbor statements are required on each device to complete this whole TCP session interaction. So there must be this nice agreement on where the session is coming from. You know, this might make a lot more sense if we go ahead and elaborate with a graphic. So let's do that now. And as you might guess, we're also going to elaborate at the command line in this particular lesson as well. Here we can see two BGP speakers configured with the correct neighbor commands, and they're going to initiate the BGP peering. We notice R1 says, all right, I'm going to initiate this session. It sends out a TCP SYN type packet sourced from its IP address from a random port number, and its destination is the destination IP address specified in the neighbor statement. And notice its source, destination port rather, is 179. Okay, makes sense. R4 says, okay, I'm going to send a TCP SYN ACK because I'm set up with a neighbor statement for the 155.146.1 device, and notice it sources the traffic from 179. Because R4 is sourcing the traffic from 179, we can think of it as the server in this client-server relationship. The destination IP address is that IP specified in the neighbor statement, and the destination port is the random port that R1 specified. Notice to close this handshaking process, R1 responds from its source address and its random source port destined for R4's 179 port, and they happily engage in their BGP peering. Notice there's lots of places that we could go wrong here. We could have the wrong IP addresses in these neighbor statements. We could have TCP connectivity issues between R1 and R4. If those addresses at the high level, if those IP addresses aren't reachable, this isn't going to work. And also, what about any kind of firewall? What about any kind of access control list that may be blocking the 179 source or the 179 destination port? Definitely something to watch out for here. So, this is the complexity that is our BGP peering process. We can learn to configure it, we'll do it quite quickly, but we really need to be thinking of what is happening behind the scenes here to make this magic of BGP peerings actually operate. Now, which device actually ends up, if you go and you configure your network statements at the same time on two devices, you have a friend help you, and you configure the neighbor statement, and your friend configures the neighbor statement. Specifically, the client role is supposed to be the router with the higher BGP router ID. It will kind of play that role of client to the TCP server. But that doesn't always work out that well. And one of the things that there are some commands that we might have a chance to look at later, actually, but there are ways to try and force which is playing the right client role and which is playing the server role. But our focus here is on making it work regardless of who is the client and who is the server. You see, if the server doesn't expect the exact session information that's coming in, it's going to refuse the BGP peering. And one of the big gotchas here is you're going to have a neighbor statement configured for the destination device. As we saw in that earlier graphic, the source has to match that neighbor statement that you configured. And that might always not be the case if there are multiple possible outgoing interfaces in the BGP routing table. We have a way to get around this, as I'll show you with the command line with the update source command, but this is a genuine concern when we have multiple paths between two devices. You've got to make sure that the actual outgoing interface matches up with that is configured in the neighbor remote AS command. This is going to make more sense if we jump to the command line, and specifically before we do that, let me show you a topology that we're going to experiment with. Look at this situation here. We want to establish our BGP peering between R4 and R5, but notice we're going to have two different, totally valid ways for R4 and R5 to reach each other. So we need to know how they are indeed going to source their traffic to each other in order to configure the neighborship properly, the neighbor peering statements properly, in order for the underlying TCP and BGP process to work. So this is a classic type of situation where, boy, we better be a bit careful in our configuration to ensure that all works right. Now, you may want to jot down, you can pause the video here and jot down this topology, or take a look at this area in your printout, because it'll make more sense as we look at the command line and experiment with BGP peerings over this type of topology. Okay, so let's go ahead and do some proof of what we have discovered here and talked about. Let's do some proof by debug, our favorite activity here in this video series, in order to kind of confirm what we've learned and what we've been talking about. Down here on R5, I'm going to do this. I'm going to say no service timestamps to kind of clean up the debug output we're going to get a little bit. I'm going to say log to the buffer. I'm going to say don't log to the console. And then I'm going to go ahead and I'm going to say let's debug IP packet detail. Wow. Definitely something that we're going to do in practice, not in production. Okay, so R5 is all set to debug. Let me go ahead and clear the log right now, make sure there's nothing in the logging buffer. All right, great. Now what we're going to do is we're going to go up to R4. And on R4, we're going to go ahead and initiate, activate. How many words can I say that end in 8? We're going to go ahead and kick in BGP. You ready? Router BGP. And then we're going to say neighbor. And we'll pick the serial interface, 155.11.45.5. And that's going to be remote AS1. So we're setting up an IBGP peering. All right. We're going to slide down to R5 and we're going to see what is going on as a result of that activity. You ready for this? Let's take a look. All right, look at this. I see some interesting output here. We were sourced a packet from R4, from the 45 interface, from serial 010, the point-to-point connection, not the frame connection, but the PPP link or whatever we got going on there, that non-frame link. We were sourced a packet from R4 destined for the destination in the neighbor statement, 155.11.45.5. It was sourced from the random port of 60717 with the destination for the BGP port of 179. Notice it was a SYN packet. Okay? Notice it was a SYN packet. Now, if we look down here, we see that we sent a packet. This is R5 sending a packet sourced from itself, destined for R4. It's sourced from the BGP port of 179, and notice it's an acknowledgement, but it's got the reset set. So this is very interesting. This R5, not configured for BGP, is saying, well, nice try, but I am not going to establish this BGP session with you. Another way to see this, and it's because R5 isn't configured with the peering statement in the reverse direction, isn't it? If we, another neat thing to see this, how BGP behaves, another neat thing you could do is we could go up to R4, and on R4 we could say telnet to 155.11.45.5 over the port 179. And immediately it says, look, port 179 is closed to you. See that? Port 179 is closed to R4. Now, if we tried that in the reverse direction, if we went down to R5 and we said telnet 155.11.45.4 port 179, it tries it. That port 179 on R4, because of our configuration, is open and listening. It's ready to go. It's ready to do the BGP session. So, very, very interesting here. We're seeing how exactly BGP works behind the scenes for these peerings. Now, of course, this is eventually going to time out. That's fine. But it does prove that the port is open, port 179, on the R4 device. Oh, come on, time out already. Because what I'd like to do next is I'd like to go ahead and I'd like to do the proper configuration on R5, and then we'll take a look at the debug output, and we'll see the peering session come up. I could have set a timeout value quicker here, so this would time out quicker. Let me see if I can break this somehow. There we go. Okay, so here we go. Router BGP1 neighbor 155.11.45.4 remote AS 1. Oh, before I do this though, let's do this. Let's go up to R4 and let's say no, we're going to say logging console. We're going to say logging buffer. No log console. No service timestamps. And we're going to end and say debug IP packet detail. Excellent. Clear log. All right, great. Now slide back down to R5. Neighbor 155.11.45.4 remote AS 1. All right. Now what we should see down here on R5 is we should see a confirmation that the BGP peering establishes. Oh, but that's actually silenced without the console logging, so it's going to actually appear in the buffer. So I can do a show IP BGP summary, and we can confirm. Oh, we're in the active state. That's a good sign. And what we should see here is we should see this go from active to established, this BGP peering. Now that both have the proper commands, and they're both pointing at each other. Watch this. Clear IP BGP asterisk. Show IP BGP summary. And there it is. Woo! Boy, that took some time, didn't it? But there it is. We established the adjacency. Okay? All right. It's so funny, isn't that? And we can learn a lot about the lab exam kind of experience right there. You kind of gauge how long it may take to form that adjacency, and you know when to get concerned. And I was starting to get concerned there, but obviously the adjacency established. Let's go look at the output that we see on R4 for that. Okay, let's see. There it is right there. The console message that we're used to seeing at the console, neighbor 155.11.45 is up. And now we can see we received, we sent a packet. We're on R4 right now. We sent a packet to R5 from the random source port to the destination of 175. We received a packet from R5 going to R4 from the source port of 179. R5 is our server destined for our random port. And you can literally see these communications, and you can see the success. Here's this push packet sourced from the BGP server, this ACK push establishing the session. So pretty cool. We can see this client and server relationship right here in the debug messages. Again, show IP BGP summary confirms that we are indeed up, and you can tell that we're up because you can see the time that we've been up here, and you can see the prefixes received. We haven't received any prefixes from the neighbor. That's our healthy status indication with BGP, isn't it? We want to see that we've been tracking how long we've been up, and we want to confirm that there's been a number of prefixes received. If we haven't configured a network statement and we're not advertising anything to each other, then of course we see 0 prefix received there. Now we know there's redundancy between these two devices. We know there's the redundant connectivity. If we look at the, just quickly show IP interface brief, we know that we can get down to that device R5 via this serial link, or we can get down to that device via this serial link. Watch this. I'm going to ping 155.11.0.5 over the frame. And that's a perfectly great alternate path. But watch what's going to happen. Watch what's going to happen. I'm going to say no logging, or I'm going to say logging console. Okay, watch what's going to happen. When I go in and down the interface that we're using for this connectivity, we're going to see we're in a world of hurt for BGP's session. We go to administratively down. The line protocol on serial 010 changes state to down. And now watch what's going to happen with BGP. BGP set up to peer between 155.1145x should fail now. And here we go. Here we go. It does indeed fail because that link referenced in the neighbor peerings has failed. We can see the failures taking place if I do a show IP BGP summary. Is it truly down yet? No. Nope. It's going to fail a number of times before it is declared down. But I think we all can see that it's going to happen. These devices are trying their best still to communicate using these sources and destinations over the BGP port. Let's show IP BGP summary again. Still up, but we're getting these repeated failures. And we should see the adjacency crash here shortly. And of course, it will throw a console message that the neighborship crashed. Now you notice again, from an exam perspective, this is pretty scary. BGP's relatively slow convergence is something that proves fairly problematic. It's fairly troublesome when you're in the certification environment. What can happen is you make some kind of a change and something is going to break, but it doesn't break right away. And that's always a little scary. We like when there's an immediate result to give us a heads up as the administrator in the lab exam that there is a problem. But here we can see it's taking a while, and bang, it just happened. If we scroll back here in the output, we see neighbor 155.1145 down, BGP notification sent. If we do our show, and look at that, there's a fin packet. There is a fin packet. It is finny. It's all over. If we do a show IP BGP summary, we see we are now stuck in active for that BGP neighborship. And gosh, what a shame we had that nice redundant connectivity between the two devices. So what a buzzkill. What a major issue here. I am so disappointed. We have this redundant connectivity between these key routers, router 4 and router 5, and we really can't seem to take advantage of that with BGP. I mean, we just saw where if the link fails that we're using for the BGP peering, the R4 and R5 lose their connectivity with each other. Well, I know what you're thinking. You're thinking, Anthony, why don't you do what the experts do, and why don't you leverage the loopbacks on R4 and R5? Why don't you peer between the loopbacks? Well, let's go ahead and give it a shot. This may be a requirement in your exam. I mean, you may not have to do this in your exam, but you certainly might be forced to do this in your exam, depending on the wording of the question. Well, let's get back to the console then, and let's try and take advantage of this redundancy with a loopback peering between R4 and R5. Here we are, back again at our devices. Let me go ahead and say undebug all, because we don't want to be bothered with all this output. I love that. We did undebug all, and we got a little bit more of the debug. It was its last dying gasp there at our console. Great. All right, what we're going to do is this. Let's say no router BGP1 on both devices. How to start over when you don't like your configuration. And let's go ahead and let's run a routing protocol between these two, because I know one thing, right now we can't reach the loopback of the devices. It's unadvertised. Here I am on R5 trying to ping the loopback of R4, and that's just not going to work. So let's go and let's add, an IGP. So I'll say router, let's pick our favorite IGP. Today, my favorite's EIGRP. Yeah, it's so swell. I love it. I love it. Network 0000. I don't care. I don't care. I don't care. I don't care. So we go ahead and run EIGRP on every darn interface down here on R5. That'll teach it. Router EIGRP 100. Network 0000. I don't care. I don't care. I don't care. I don't care. And we should see a pretty quick adjacency come up. That's because EIGRP, unlike BGP, converges so darn fast. Now I bet we can reach the loopbacks. And lo and behold, what's going on here? I didn't expect that failure. I did not expect that failure. Show IP route for EIGRP. Let's see here. We got some automatic summarization going on. Ooh, I was a little too quick. No auto on R5. No auto. That dreaded automatic summarization. Let's see, where's my ping? Is it still in there? No, I got to do it again. Ping 150.11.4.4. Boy, aren't these ping tests important before you go and add some other layer of complexity? You know me, I love to configure in my baby steps, and we just saw why. All right, so here in R5, I'm going to say router BGP1. My neighbor, my very good neighbor, is 150.11.4.4 remote AS1. Now look, I am saying that I expect the traffic to come from 150.11.4.4. The other side is going to end up expecting it to come from 150.11.5.5. The traffic is never, ever, ever, ever going to be sourced from the loopbacks by default. So I better go ahead and say neighbor 150.11.4.4 update source loopback 0. Now we see the need, the necessity for that command based on our earlier investigations, and we'll never forget it again. So I say router BGP1. I'm getting real excited here. Neighbor 150.11.5.5 remote AS. Whoa, that's not going to work. No. Do it again. Say 1. The peering's not going to work until we do the update source over here. And I've made some kind of configuration error. And what have I done? Let's see. It has something to do with, let's do this. Exit. I didn't have to exit. Do show run section BGP. It didn't take my neighbor command. All right, router BGP1. Let's try it again. From the top. 150.11.5.5 remote AS1. And now, retype that and simply say update source loopback 0. And now we should have a happy BGP adjacency, and it's redundant Show IP interface brief. Notice we're still administratively down on this interface. I can say router interface serial 010. Interface serial 010. I can say no shut. Now both interfaces up here are up. Great. We just had EIGRP go adjacent over there. I can go to the serial 000. I can shut it. We'll lose the EIGRP adjacency there, but we still have the other one. And of course, we're still going to have the BGP relationship. The BGP relationship will be flexible now, based on the interfaces that are up, because of that beautiful best practice in the real world of peering between the loopbacks. Do we have to do it in the lab? No, we don't have to do it in the lab. We would do it if they explicitly or implicitly ask us to do it in the lab. Now, if we were to do that same demonstration, but using eBGP, we would have to add the eBGP multi-hop command. Because when you see with eBGP peerings, when you're peering between different ASs, you're going to see as we move throughout this class that it's assumed to be directly connected. And the loopback interfaces will never appear to be directly connected. So we're going to have to use the multi-hop command in order to do that nice redundant peering in an eBGP environment. So we do the update source still, and we also have to do the neighbor multi-hop command. Now, one of the loop prevention pieces for eBGP is to drop any prefixes that are showing up with your own AS in the path. What a nice little loop prevention. It says, whoa, that prefix passed through me at some point. I'm not going to let it in. Everything in BGP can be modified, it seems like. And sure enough, there's a neighbor allow AS in for the rare cases where you actually want the prefix to come back into your autonomous system. As we'll see with eBGP peerings, each time the prefix is handed off from AS to AS, the next hop changes from one AS to the other. It's literally saying, hi, here you go, here's your prefix, and I'm your next hop because I'm the entrance to this AS. And then that device will hand it off to its next eBGP peer and say, hey, I just changed the next hop because I'm the entrance to your next AS. So the next hop changes to the entrance point for the AS. So it's an AS to AS routing protocol, as we discussed earlier. We'll also see as we work through the content in BGP that there's IBGP peering rules. The biggest one, well, first of all, let's talk about the easy one. When IBGP peers pass off the prefixes, it's not an eBGP peering, so there is not that next hop modification that we know the eBGP peers are going to do. All right, simple. But the one that we're going to spend some time on is called the IBGP split horizon rule. It's loop prevention via route suppression. What happens is when an IBGP speaker learns of a route, okay, it will, from a IBGP neighbor, okay, so when one IBGP neighbor passes an IBGP route to the next, it won't turn around and send it on to any other IBGP peer. So IBGP learned routes are never advertised to other IBGP peers. That's really how we remember it. It's that simple. When we learn an IBGP prefix, we don't send it to other IBGP peers. Very, very interesting. This is called the IBGP split horizon rule. And this implies that inside our cloud we have a full mesh of IBGP peerings, or we have a clever trick. And the tricks that we're going to teach you in this class are route reflection and or confederation. And we'll take a look at those in upcoming lessons. So boy, BGP, it's definitely complex, and we've seen quite a bit of complexity involved in just this overview and lesson on peerings.